Hello everyone, today we're going to be going over an example problem that pertains to Reynolds number and viscous pipe flow. So in this particular problem we have oil with a kinematic viscosity of 0.007 square feet per second flowing in a 0.25 foot diameter pipe at a volumetric flow rate of 0.01 cubic feet per second. This problem asks us to determine the head loss per unit length of pipe for this flow. Okay, so as you can see we have a lot of fundamental characteristics that define our fluid flow through our pipe. So the first step that we're going to go ahead and take is we're going to go ahead and calculate the Reynolds number. We know the volumetric flow rate. We also know the area, so we also know the diameter, so we can go ahead and calculate the area, which will help us determine the velocity. And we also know the kinematic viscosity for the fluid going through our pipe. So we have all of the key characteristics, the key quantities that we need in order to go ahead and solve for the Reynolds number. So let's go ahead and do that first. So we have our Reynolds number is equal to velocity times diameter divided by our kinematic viscosity, nu. Now, in our problem though, we have it such that we're given the volumetric flow rate, not the velocity of the free flow. So what we have to do is we have to use the definition of the volumetric flow rate to assist us in going ahead and calculating the velocity and therefore the Reynolds number. So we know that the volumetric flow rate is the velocity times area. So if we go ahead and solve this for velocity, we get the volumetric flow rate divided by area. And we can further expand this by replacing our area with pi over 4 d squared. And what we end up getting is 4 divided by pi times v dot divided by our diameter squared. So now we have our velocity in terms of quantities that we know. So our volumetric flow rate and the diameter of our pipe. So what we can do now is we can go ahead and plug this expression in to our expression for Reynolds number. So what we end up getting is we have Reynolds number is equal to 4 divided by pi times v dot times d divided by d squared times our kinematic viscosity, nu. So one of our diameters goes ahead and cancels out, which means that our final expression is 4 divided by pi times v dot divided by d times our kinematic viscosity, nu. So now we have our Reynolds number in terms of all things that we know in our problem. So if we go ahead and plug in all of our known values, what we end up getting for Reynolds number is 7.28, which is a very, very, very small Reynolds number. It's quite a small Reynolds number, and it's significantly smaller than 2100, which means that for this particular case we have laminar pipe flow. So since we have a Reynolds number that's less than 2100, we have laminar flow. Now, in these particular problems, it's incredibly important to calculate Reynolds number as soon as you can. By calculating Reynolds number, you can determine whether or not your pipe flow is laminar or turbulent, and this will assist you in helping determine which equations you can actually go ahead and use to determine things like the entrance length or your Darcy friction factor, because the expressions that you need to use to calculate those will be completely dependent upon whether or not you have laminar flow or turbulent flow. So by going ahead and just immediately trying to calculate the Reynolds number, calculating the Reynolds number as soon as possible, you can determine which equation sets you can use for, calculating the Darcy friction factor or entrance length for your pipe. Okay, so we have our Reynolds number. We know our pipe flow is laminar, and we know that we now need to go ahead and calculate the head loss per unit length of pipe for our pipe flow. So let's go ahead and write down the Darcy-Weisbach equation. So step number 2. So we have head loss is equal to our Darcy friction factor times the length of our pipe. So we have the length of our pipe divided by the diameter of our pipe times V squared divided by 2G. Okay. So in this problem, it asks us. Sorry, I'm having trouble speaking. So in this problem, it asks us to solve for the head loss per unit length. So let's go ahead and rearrange our expression so we have head loss per unit length. So we'll just divide through by length. So what we end up getting is we have head loss divided by length is equal to our Darcy friction factor times 1 divided by our diameter, V squared divided by 2G. Okay, so just as we did before for the Reynolds number, so we have our expression for velocity in terms of its volumetric flow rate divided by area. And now we can go ahead and take that expression and plug that into our expression here for our head loss per unit length of pipe. Okay, so what we end up getting is we have our Darcy friction factor times 1 divided by our diameter, 4 over pi squared, times the square of our volumetric flow rate divided by 2G d to the 4th. Let me rewrite that. Might be a little hard to see. So our diameter to the 4th. Okay? So simplifying this, what we end up getting is we have our Darcy friction factor divided by diameter to the 5th times 4 divided by pi squared, v dot squared divided by 2g. Okay, so now we have our final expression in terms of all things that we know with the exception of one quantity, which is our Darcy friction factor, F. So now we need to determine what F is. So luckily we've already gone ahead and calculated our Reynolds number. Using that, we've also determined that we have laminar flow in our pipe. So now we know exactly how we need to calculate our Darcy friction factor, which for the case of laminar flow is actually really simple. We just use the relationship 64 divided by the Reynolds number to calculate our Darcy friction factor. So, since we know our pipe flow is laminar, we can determine our Darcy friction factor by just 64 divided by the Reynolds number, which we already have calculated, and we already had that calculated in step 1. So if we go ahead and plug that in to our expression, what we end up getting for our Darcy friction factor is 8.796 for our Darcy friction factor. Okay, so now we have all of our knowns. We have diameter, Darcy friction factor, volumetric flow rate, we know gravity obviously, and now we can go ahead and plug those into our expression. So we can plug all of our knowns into our expression that we derived in step number 2, and we end up getting, so finally, plugging all those values in, we get that our head loss per unit length of pipe is going to be 0.022, rewrite that a little bit, so 22 feet per unit foot of pipe. So this is non-dimensional, but I just wanted to explicitly say that it's foot per unit foot of pipe, so that if you wanted to go ahead and use this to calculate something, you know that it's the head loss per unit of foot per pipe. So it's just the head loss per unit length of the pipe. So it's explicitly defined in both the actual right or left hand side, so HL divided by the length of the pipe, and it's also explicitly defined in terms of our units. So our units would be non-dimensional here, but I'm just writing it out as foot per unit length, foot of pipe, just so it's explicitly defined that this L here is the length of pipe. Okay, so, but yeah, but in reality, you don't actually have to put, foot per unit foot of pipe since it's a non-dimensional parameter. I'm just doing this out of my own practice. Okay, so that is the end result for our problem. So right here. And actually, I'll just write it as non-dimensional as well. So we have, or just write it as a unitless quantity. Both are exactly the same. Just one's more explicit than the other. Okay, so that is our final answer for this problem. We've gone ahead and solved through our problem. So not too bad, not too bad. So hopefully you found this video to be helpful. If you have any comments or questions regarding the solution or any of the assumptions that we made in the problem, go ahead and leave a comment in the comment section below, and I will respond to your comment as soon as I can. Again, hopefully this was helpful. Thank you for watching, and I will see you guys next time.